We're now going to talk about the numerical solution using our good old split step. Our split step spectral method. So you've actually done this as an exercise in the previous all right, there's our equation. So we just solve each time step in turn, and we do it in the Fourier space because it's much better, because we have dt of u hat. I probably should use a different colour for the Fourier space, but I haven't done that. So this is a half minus a half, sorry, I've got a minus here missing, k times the ik times u squared hat plus z minus, because it's ik squared, minus k squared u hat. Okay, so we can solve these in turn. Get the right colour here. So dt of u hat equals minus k squared u hat. Well, that's easy, isn't it? That's u of t plus delta t is just u, and we can solve this exactly, at least in Fourier space, e to the power of minus k squared u hat. I remember we use a function of u hat as a function of t and k. K is the variable here. Maybe I should have written that in just to be really clear. K and t. Alright, so that's that one done, and then the other one, dt of u hat is minus a half ik u squared Fourier transform. Well, we've got to do this by some kind of stepping, right? So we've got to take the Fourier transform. So we get u hat, I'm just going to write it as t plus delta t here, is equal to u hat of t plus, in this case minus because of the minus sign, minus delta t times ik over 2 times the Fourier transform of the inverse Fourier transform of u hat, and then squared. Okay, so you take the Fourier transform, you're solving Fourier space, you're time stepping in Fourier space, but you inverse Fourier transform it, square it, Fourier transform it again, multiply it by ik, and then time step by that amount. And then you've got the solution. As simple as that. Let me just talk a little bit to the notes. There's the solution of the so it's got a direction of flow built into the equation. It wants to go this way. So these are the and that's the travelling wave solution. You can see it's sort of steepening here, but then being held off by the diffusion. We're starting with a block, right? The can only get so steep here, and the diffusion holds it off. The second derivative is really high at these bending points where it bends. There's the solution calculated. So we've only got one thing left to do here, and that's calculate the exact solution.